Hey learners, Jared here, and welcome to the video walkthrough of your Forces Test 1. The first question on this test is the hanging mass video walkthrough, which is a separate video. So this is starting with your second free response. So we have a motion detector watching a cart, and that cart is getting pulled along to the right. The acceleration of the cart is in the positive direction, so the cart is accelerating from this pulling force, and we've got a table of data there with force sensor reading and then the acceleration of the cart from that motion detector. And part A is just draw and label all of the forces that are acting on the cart. So we have tension from the string. We've got the weight of the cart. We've got the normal force from the track. And then we would have some kinetic friction present. Not equal to the tension because we do have an acceleration with that cart. So this part is worth 3 points altogether. You got a point for tension, you got a point for friction, and then you got a point for both of your vertical forces on your cart. The next part is taking this data, and there wasn't a grid provided, but you could have used your own graph paper, or you could have even used Desmos, which is what I did, and plot acceleration as a function of time. So acceleration is our vertical axis. So let me add in that graph. And the point breakdown for this was I would need to label my axis. So here is acceleration, and that is meters per second squared. Here is force measured in newtons. I've got my data plotted, and that got you 3 points with the line of best fit for that. So part B was worth 3 points. One for drawing the graph and plotting things correctly, drawing a straight line, and then labeling your axes. The next part is using the straight line, calculate the mass of the cart. So this is showing acceleration and then the force on that force sensor. So the summation of our forces is equal to an object's mass times its acceleration. And the mass of the cart, since we're looking at acceleration versus force, so we're looking at it like this. Acceleration, is 1 over m times the summation of our forces. So our slope is equal to 1 over m. And you can see my slope right there. It's 2.12. That equals my slope, but that is 1 over my mass. So by flipping that slope, mass is equal to 1 over 2.12, which is about 0.472 kilograms. So the point breakdown for this was if I saw just some means of you getting the slope of your line of best fit, that got you a point. And then for setting that slope equal to the reciprocal of mass, that got you the next point. Using the straight line graph, determine the magnitude of the force of friction. So you've got this force being applied until you get to the actual acceleration of the cart. So you're applying, it looks like about 0.27 newtons of force before you actually, get any acceleration. So that x, this is part C, so that x-intercept is your frictional force, Fk. And so that is 0.272 is what I would do for 3 sig figs newtons. So that takes care of part, sorry, that was B, I. The graph is I, and then right here is II. Okay. The next part is we're looking at, it's repeated. The force sensor reading is 0.45 right here. The experiment is repeated, a constant force sensor reading of 0.45. The cart starts from rest and is pulled for 2 seconds along the track. So determine the acceleration of the cart. And to do that, you would need to know, so this is part C, I. We want to know the acceleration. And that acceleration is coming from the tension minus how much kinetic friction you have. And that equals mass times acceleration. And so for that, if you had the summation of your forces, and where you earn the point is actually knowing what those forces are doing. So Ft minus Fk. You didn't even have to really calculate the acceleration to get the correct answer, but your acceleration is 0.376 meters per second squared, using this value for friction and then that value for tension that they gave us in the problem of 0.45 newtons. The next part, the string breaks at 2 seconds. How much time does it take for the cart to come to a stop? So this is literally a like V final squared is V initial squared plus 2A delta. Oh, no, we're trying to figure out time. I'm sorry. I was going to calculate how far it went. V final is V initial plus a t. We're solving for time. The initial velocity is how fast it got going after that 2 seconds. And then V final is going to be 0. Now, the acceleration is going to be different because the new acceleration is now just from friction. So friction is the only acceleration, or the only force that's causing that acceleration. And when you plug in all of your values, so you solve for, because you got to know what your like your final velocity is for that first 2 seconds. So at 2 seconds of this acceleration, what's your velocity? But when you do that, you will get a time of about 1.28 seconds. This V initial is just double that acceleration. So that's 0.752 meters per second. And then you're solving for that time with this new acceleration. So this part was worth 3 seconds all together. You got a point for figuring out the velocity there. You got another point for recognizing that you got a new acceleration being caused by friction. And then the final point comes from actually solving for time. Okay, in the next part, the experiments and analysis in parts A and B are repeated with a cart that has the same mass but a greater amount of friction. will the slope of your new line be greater than, less than, equal to, or the same? Justify your answer. So the slope of our graph wasn't determined by the friction. The slope of our graph was determined by the mass, specifically the reciprocal of mass. What's going to change is this graph would just shift over, but it would still have the same slope. It's just going to have more friction. So for this last part, it is equal to, and then will the horizontal intercept of the new line be greater than? So that's where that change comes in, and that's where that greater than comes in. So that's a walkthrough of the second question of the first version of our forces test.